We've been integrating, and this seems like a shift in gears, although we will get back to integrating in a few videos. For now, today we are talking about approximating polynomials. First of all, what is a polynomial? A polynomial is some function, let's say p of x, that has the following form. So we have a0 plus a1x plus a2x squared all the way out to, let's say, a dx to the d. We may write this in summation notation as follows. It's a sum, let's say k equals 0 to d of ak x to the k. This is a polynomial where the degree, the largest k, such that ak is not equal to 0. And here in the above one, this is degree d above, okay? Well, it is degree d provided that this part, I'm assuming that this a sub d is not equal to 0, and then we have a degree d polynomial. But you could have some of the coefficients before then could be 0. This is fine. We would still be degree d. Okay, this is probably something you're comfortable with. Well, let's define some more things. So definition, the partial sum I will use this notation, p sub n of x. Well, all you do is you just add up of this ak x to the k. So you add up all of the terms up to degree n. So for example, let's do an example quickly and then we will move into some other things. If we take the polynomial p of x, which is 5 minus x squared plus 3x cubed plus 6x to the fifth. Okay, this is degree 5, right? We have p0 of x is just 5. p1 of x is also 5 because we have no x to the 1 power. p2 of x is 5 minus x squared. p3 of x is 5 minus x squared plus 3x cubed. And then we have, sorry about that, we have two more, at least, that I'll write. p4 of x is the same thing as p3, 5 minus x squared plus 3x cubed. This is the fourth. Oh, I should put that in the definition, I will. And then p5 of x is the entire polynomial. And if I wanted a p6, p7, p8, those partial sums, it would also be the entire polynomial. Now let me add this to the definition, what I was just saying. This is the partial sum of order n, or you might say the nth order partial sum is here. You add up all the terms up to degree n, like this. Okay, one more definition. Definition, a polynomial centered at a. So this is what I'm defining. Has the form, well, maybe I'll call this one q of x. Well, it is a polynomial, but it has a different form than the form that I gave before I erased. So this will be, for example, c0 plus c1 x minus a plus c2 x minus a squared, all the way out to, if it's degree d x minus a to the d, Okay, where this c sub d, this coefficient, is not equal to 0, or if it is not equal to 0, then this would have degree d, just like the last one. What's different here is this is a little bit more general of a form. A here can be any real number. If you take a equals 0, then this is the exact polynomial that I had on the board before, and the way maybe you're used to looking at polynomials. But similarly here, similarly we have the nth order partial sum, which we add up to n of ck x minus a to the k. Okay, now, why in the world are we talking about polynomials when in calculus we are interested in all kinds of continuous and differentiable and integrable functions? Well, here's the idea, is that polynomials are easy to work with. For example, differentiate a polynomial, integrate a polynomial, take the limit of a polynomial. What else would we even need to do? Those are the three things we do in calculus, right? Or the three big things. These are all very easy. In fact, the first rules you learned for differentiating, integrating were for polynomials. It's a power rule. Okay, polynomials are easy to work with, whereas more general functions, not necessarily easy to work with. Okay, polynomials are easy to work with, so we want to work with them. So today we are going to discuss polynomials centered at A, and some things like this. And at first, I'm going to practice approximating a polynomial with a polynomial, which seems strange because I've already said polynomials are easy to work with. Why are we approximating a polynomial with another polynomial? Well, it's really just to build this idea and this technique now. And in the next video, we will start doing the exact same thing, but it will be for more general functions. So we will be approximating more general, more complicated functions with polynomials. And this video is kind of just the warm-up and discussing the concepts and working with them some. Okay, now one more comment to make is that notice the following. If you look at, say, a polynomial centered at A, okay, when x is very close to A, the center, what dominates? Well, the lowest powers in the polynomial dominate. And this is a very good observation, and we even used it, for example, in Calc 1, which I will get to momentarily. It's quite the opposite of when x is very far away from A. If x is very far away from A, then the highest powers dominate. But when x is very close to A, it's the lowest powers that dominate because, well, this quantity is very small, and when you raise it to the d, it's really, really small. So the lowest powers will dominate. And this is an important thing to think about as we approximate functions with polynomials. Okay, now, let me see. I want to do an example. So suppose we have p of x, which is 3 plus 2x squared minus 3x to the 4th plus x to the 5th. Okay, and we would like to approximate, let's approximate the function nearby x equals 2. Well, how would you do this? I mean, one way, this is not even calculus, you might think, well, just evaluate the function at x equals 2. And and it's continuous, so it's going to be nearby the function value. Well, okay, maybe we'll compute the function value anyway, so one idea, okay, just evaluate the function, although I'm going to do something else. P of 2. Well, this is 3 plus, this is going to be 4 times 2 minus, this is a 3 times 16, and then plus 2 to the 5th, 32. So if we have a 11 and 32, 43 minus, this is 32 and 16 gives me 48, negative 5, okay? So you might say, well, the value, negative 5, that's a good approximation nearby. But we know, for example, calculus 1, there's a better approximation than this, right? Which is, okay, tangent line, right? This is the best linear approximation to a function nearby some value, okay? So let's calculate this. We know the tangent line. Yay! Okay, I love calculus 1. The tangent line, this is the best linear approximation to y equals p of x near, well, now I know the point. The point is 2 comma negative 5. Okay, now let's calculate the tangent line, or an equation of the tangent line, I should say, in this case. And then we will notice something about it, and we will move on with talking about these polynomials, because it's really important observation to see the tangent line, I think. Well, we have a point, the one point on the line. Every point, right, or every line, we need a point, a slope. Then we can get an equation of the line. Our point is 2 comma minus 5. I know the slope will be the derivative evaluated at 2. Okay, then I can get an equation, for example. So let's take the derivative. Okay, here we go. 4x minus 12x cubed plus 5x to the 4th. Now let us evaluate at 2. This will give us the slope of our tangent line. Well, this is 8 minus 12 times 8 plus 5 times, well, 2 to the 4th is 16. Now let's see what we can do here. This is 8 minus 96, and then plus 50 and 30 makes 80. So we have 88 minus 96. This gives me negative 8. Okay, this is the slope, negative 8. Okay, now let's write the equation of our tangent line. Well, we have point, we have slope, y minus y1 is x minus x1. Except I'm not going to look at it like this. Let me just rewrite this slightly to make my point. Okay, I can. This is a plus 5. If I move the 5 on the other side, it will be a minus 5. Then I have minus 8, x minus 2. Okay, what do we see here? Well, first of all, this is an equation of the tangent line to p of x at x equals 2, right? That we have calculated. But it's also, look at the form, and in light of what we have just been discussing, it's a polynomial centered at 2, okay? This is, maybe I will put that in stars in red. This is a polynomial. It's a degree 1. Degree 1 polynomial centered at x equals 2. And moreover, if you took, let's see, the order 0 partial sum, which is just that first piece, you get this sort of maybe the common sense approximation. Just evaluate the function, right? And this is the best linear approximation. Generally, what does the tangent line look like? So now maybe I'll put a line and I will write generally. If you have a polynomial p of x, okay, and you have a point a comma p of a. So the tangent line has the form y equals, well, it's p of a plus p prime of a x minus a. And you notice that very generally, in fact, I don't even need polynomial here, but today I'm talking about polynomials. Very generally, the tangent line is a degree 1 polynomial centered at a. Okay, and we see this coefficient is just a function value. This coefficient is the first derivative, both evaluated at a. Okay, I want to work more generally now. We just saw in that example, we had a degree 5 polynomial, and I said, well, what would be the best linear approximation? Of course, tangent line. And we saw this tangent line was a polynomial centered at 2, which was where I was trying to get my approximation around. Okay, now I'm going to work more generally. I could work degree D, although I'm just going to save myself some time by just working degree 4, but everything I say, well, you will see, it generalizes. So let's suppose I have some polynomial of degree 4, and then, of course, this is the tangent line given some a real number, and this gives the best linear approximation to my polynomial near x equals a, right? This we discussed. Okay, now what I want to do now is make an observation. There exists a, well, if this is degree 4, this will be degree 4, polynomial q of x, and q of x will equal q of x with q of x will literally be equal to my polynomial, and this p of a plus p prime of a x minus a is the first order partial sum of q of x. Okay? Now, you will see things like this in your homework. It'll give you a polynomial, and it'll say, rewrite this polynomial as a polynomial centered at, and then there's some a value. Okay, this is what you're going to do, although I am going to show you what the coefficients must look like. Well, okay, so let's suppose q of x, well, it's a degree 4. I'm just making a degree 4 polynomial centered at a, and then I will figure out what the coefficients must be. Okay, so q of x equals, it's b0 plus b1 x minus a plus b2 x minus a squared plus b3 x minus a cubed plus b4 x minus a to the 4th. This is my general, or is a general polynomial of degree 4 centered at a. Now, okay, I want this to be equal to p of x. P of x, which is some degree 4 polynomial. Well, if you look at this, the first thing we can do, just evaluate at a. Okay, and you get that, well, here, now this is my q of x. I'm evaluating this part. Well, look, b0 plus, Well, evaluate at A, 0. Evaluate at A, 0. 0, 0, because A minus A is 0. So we get B0 plus 0 is equal to P of A. Immediately we solve. Well, we've solved it here. That this constant piece, B0, is P of A. Maybe I will put red boxes around as I solve for my coefficients. Okay. And you see that here, right? I said this was the first order partial sum. So we should have P of A here. We should see P prime of A for, let's see, B1. But I will calculate the B2, B3, B4 like this. Then I will mention how it works generally. Okay, well, now we have solved for one of them. What am I going to do now? Well, I have this big expression. I can take the derivative. Differentiating polynomials is easy-ish. I mean, it's the easiest things we take derivatives of. So this term becomes 0. I take the derivative here and I get B1. So what have I done? Maybe I'll write in blue what I'm doing. Take the derivative. And then I'll write in black the line. Matches above. Very nice. This is B1. This is 2B2 x minus A. This is 3B3 x minus A squared. This is 4B4 x minus A cubed. Okay? That's taking the derivative of this. Then I take the derivative here, and this will equal P prime of x. Okay? And now you see, I look here, I can't evaluate again at A. Okay, but this term remains. This term, 0, 0, 0. So I get that B1. See, now I have solved for another coefficient. Maybe I'll evaluate at A here. I'll write it above. Evaluate at A. Below, we get that B1, 0 equals P prime of A. So we get B1 is P prime of A. And then box it in red. Okay, I'm trying to make this match. Box it in red. Box it in red. And we see that here so far, right? So far, so good. We have B0 plus B1 x minus A. This will be the first order partial sum of whatever we get coming next. Well, guess what? This continues. We're going to take the derivative again. We take the derivative again. What do we get? Take the derivative. We get 2B2 plus, we have a 3 times 2, B3 x minus A, plus 4 times 3, B4 x minus A squared. This should be the second derivative of x. Okay? Well, now, probably, hopefully, you see my trick. Again, evaluate at 0. What do we get from this? We get that, evaluate at A, so that this is 0 and this is 0. And here we will get that 2B2 is P double prime at A. Or if you divide, you get that B2 is the second derivative at A over 2. Okay, well, I'm going to move up here, take this line, I'll star it, this line, and I will take the derivative. I'll write this, and especially since I'm moving, take the derivative. And what do I get? The left-hand side here, I get 3 times 2 times B3 plus 4 times 3 times 2, B4, x minus A, and this will equal, well, I take the derivative again. This is going to be the 3rd derivative at x, okay? Evaluate at A. Okay, this term now vanishes. So we get 3 times 2. B3 is the third derivative at A. Okay, and now solving here, we get B3 equals the third derivative at A over, well, this is 3 factorial, okay? Factorial, what is n factorial? You take n, well, positive integer n times n minus 1 times n minus 2. Maybe I will make a box for this. This is a side work box that I will erase. So n factorial is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. This is for positive integers n, and we add that 0 factorial is 1. It sort of has to be, okay? This is just defined to be this way, okay? So this we see 3 factorial, 3 times 2, well, times 1, 3 factorial, okay? Now we have one more because I decided to only do degree 4 here. We have one more to calculate, which is B4. It'll be our very last coefficient. And then I will come back here and I'll be able to write out Q of X. Okay. Then we'll do a few examples, okay? I know at the moment it's abstract, but once you see the pattern, you can just jump into it. You don't have to redo what I'm doing at the moment. So let's take the derivative one more time. One more time, and we get 4 times 3 times 2 times B4, take the derivative, is P, the fourth derivative, at X. Well, this is a constant, but I will just say evaluate at A, okay, because really we're going to be working with things that are higher degrees, and so this will be a constant. So if I evaluate at A or if I evaluate at any number, we'd get the same thing, but I'm going to show you the general, say, formula I will mention. So if we evaluate at A, we are following our same thing. For example, if I had a degree 5 polynomial, I would have more terms here, and I would need to evaluate at A. Then we get, maybe I will just go ahead and write B4. This will be the fourth derivative at A over 4 factorial. Okay, so this polynomial is, let me write the polynomial, and then we will do some examples. If I lost you in the last few moments calculating the coefficients, BI, well, wake back up, okay? Because we're about to do some hands-on examples. But these coefficients will come up when we do the Taylor polynomials, Maclaurin polynomials for more general functions. That's why I really like to go through the details when we're thinking only about polynomials, because they're easier functions to think about. Okay, so this Q of X is the following. What did we find? We found it's P of A plus P prime of A plus we had the second derivative at A over, well, we had over 2, but I can write it like this. 2 equals 2 factorial. We had x minus a squared. We had the third derivative at A over 3 factorial, x minus a cubed. And then we had the, I'm running out of space, the fourth derivative at A over 4 factorial, x minus a to the fourth. This is a way that you can rewrite P in terms of a polynomial centered at A, and such that, no it's not, I left off, let me back it up. P of A. I hope you caught my mistake. I didn't have a x minus a here. I didn't have this part. Now this is correct. I have all of my x minus a to a powers, and I have my coefficients. You could even write this over 1 factorial and over 0 factorial, and I haven't changed anything, just the pattern works. Or you can write this in summation notation. K goes from 0 to 4 of the kth derivative at a over k factorial times x minus a to the k. Now, take a deep breath, right? When I have taught this with the in-person classes, this section, people are like, why are you doing this? And then when the next section starts, you start to understand. I'm really building machinery for Taylor polynomials, Maclaurin polynomials, Taylor series, Maclaurin series, but we're starting with the concepts with just polynomials. In any case, what this is, you start with a polynomial p, which can be centered at 0 or literally any other number. And now I want to rewrite it as a polynomial centered at a, where they're physically equal. Okay, so this q of x is literally equal to p of x. It's how we constructed it. And the coefficients have this form where you take the kth derivative, evaluate it at your center over k factorial times x minus center to the k. Okay, this is the way we were sort of constructing it. Well, I've written this as degree 4. But this would work if you had a degree d polynomial. The only thing that would change, well, you would add up to, you would keep going to degree d, and this sum would just go to degree d. Okay, it was enough. We kept taking derivatives enough times to stop at 4. Now, what's my other comment? Then we'll do two examples maybe. Okay, you see, if you look here, the first order partial sum, this was the tangent line, first order partial sum. Best linear approximation to the polynomial nearby x equals a. If you took the second order partial sum, that goes through this term, the squared, right? This would be, this polynomial sort of cut off here is the best quadratic approximation to your polynomial function more generally, nearby x equals a. And similarly, if you cut it off here, this is the third order partial sum. This would be the best cubic approximation to your polynomial nearby x equals a, like this. So these partial sums are giving you approximations, and as I mentioned, these nearby x equals a, these lower powers dominate anyway, so even taking the first 3 terms, say, or even the first 2 as you did in Calc 1, nearby x equals a, this is a pretty good approximation. This example is really just a warm-up, and it's one that we can physically see. The two polynomials are literally equal. We want to rewrite, this is just f of x is x, okay? It's f of x is x. But let's rewrite it as a polynomial centered at 2. Well, this is degree 1, right? And this, I will show you the little chart that I make, especially as we move into the Taylor and Maclaurin polynomials and series. So then I take the kth derivative at the center, kth derivative at the center over k factorial. Now this seems like a big machine just to hit little f of x is x, but I'm showing you the idea. How do we do this kind of thing on a very simple example? Okay, well, this is degree 1, so all I need is to go through degree 1. This is the original function, and then this is the derivative. Then I evaluate at the center, evaluate the center over k factorial, like this. Okay, then here is my polynomial. In fact, I'll call it q of x, is fine, which is rewriting. I should get literally the exact same polynomial. It should be x, but it's rewritten so that we see the centered at 2. And here, it's this plus this x minus 2, right? Well, not check, right? You can. This is why we started with such a simple example is you can multiply. You see this is x, 2 minus 2, we get 0. So you see we are literally, f of x is x, but it's rewritten, okay? Here we go again. I make my chart. I have, let's say, p, the kth derivative at x. Oh, I'm going to need space for this because we have a lot of terms. Then we have the kth derivative. Well, maybe I don't need quite that much space. Okay. Then we have the kth derivative at 3. Then we have the kth derivative at 3 divided by k factorial. And this polynomial is degree 3, so I need to, my polynomial I create will be degree 3, and we will see if I take the first order partial sum, it's going to be the tangent line at a equals 3. If I took my second order partial sum, it'd be the best quadratic polynomial nearby a equals 3, like this. And these are the coefficients. The kth derivative evaluated at the center divided by k factorial. That's what this calculation was showing, right? Okay, so here we go. First of all, I'm just going to fill out my derivatives. So this is my original function. Then I start taking derivatives. 1 plus 6x minus 3x squared. Take derivative again. I get 6 minus 6x. Take the derivative again, negative 6. Okay? Now I go this column. I evaluate all of these at 3. Oh, I might need more space for this. Maybe if I need a little side work box, I'll do it down below. If I evaluate my original function at 3, I get 1 plus 3 plus 3 times 9 minus 27. Well, this is 27 minus 27. It's just 1 plus 3, which is 4. Okay. If I evaluate this at 3, I get 1 plus 18 minus 27. This is 19 minus 27. This gives me negative 8. Negative 8. Now the other two at 3, I think I don't need to write at the bottom. Oh, well, this is going to be 6 minus, maybe this one I will, 6 minus 18. Okay, not too bad. Negative 12. Negative 12. And then this one's negative 6. Okay, I evaluate each one at 3, and then finally, I evaluate at 3 divided by k factorial. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, so this is going to be minus 6. 3 factorial is 6, so this is going to be minus 1. Now I am ready. These are the coefficients in my polynomial. And even when we get to the next video, and the only thing that will change when we start talking about Taylor and Maclaurin polynomials is instead of having a polynomial here, we'll have a more general function. But I'll still make these charts, okay? So here we go. My q of x, say, where I just rewrite this polynomial to be centered at 3, it's going to be 4 minus 8. Now it's x minus the center. Minus 6, x minus the center squared, minus 1, x minus the center cubed. Okay, this is my polynomial, and as long as I haven't made a mistake, well, let's check my notes while I'm at it. I have 4 minus 8 minus 6 minus 1. Okay, well, it matches my notes. So this polynomial is literally equal to this one, okay, where this is a minus. Except it's centered. We've changed the center. We've rewritten this polynomial as a polynomial centered at 3. So we are looking at the graph of this polynomial. 1 plus x plus 3x squared minus x cubed. And here is the point, 3, 4 on the graph. So if we look at the tangent line, we see this is the best linear approximation to my polynomial nearby x equals 3. This is calculus 1, but this is the first order partial sum of this polynomial that we made by taking the kth derivative, evaluating at the center, divided by k factorial. And then you take the second order partial sum, and you see it here. This is, now I've erased the tangent line, but this is a better approximation nearby, and this will be the best second order approximation, or best, I should say, quadratic approximation of my polynomial nearby x equals 3. And then finally, the third order, it's here in blue, and we see it is exactly equal to our polynomial, right? They're both degree 3, okay? So this is what I wanted to show you. And if you're thinking, why in the world are we doing this? Well, of course, I mentioned at the beginning, polynomials are very nice because they're easy to work with, okay? But ultimately, we don't want to just approximate polynomials with other polynomials if polynomials are already easy to work with. Well, this is not the goal. What we want to do is approximate more general functions, any functions as complicated as you want to make, as long as they are differentiable. We want to approximate those functions with polynomials. And this is the topic of the very next lesson.